Okay. So we are learning about the system value. Okay. Then, so actually in the previous class, I intensively explained about the test bench. So, because this is the unique design flow for this the system design actually. So it means that actually so if you use any normal programming languages, then actually you don't need to you don't need to generate test bench, right? So you can just add some print function in your program code, and you can check the contents of the variables, right? But the system value, so it's a design, the digital design flow is a little bit different. So we require test bench, and then so this is the structure of the test bench. So test bench includes the design on the test module, okay, DUT module. So actually you need to design DUT also. And then also you need to design the test bench. So in the test bench, you need to specify input stimulus. So input stimulus means that input values, and then these input values change by time. So you can specify input signals, and then you can check the output signals. Output signals determined by input signals. That is the test bench. Okay. So because this is the unique design flow of the design, I intensively explained about the test bench in the previous class. Okay, so we are now. So in this class, so we will learn about the syntaxes and then some operators of SystemVerilog. Okay, so we are learning about the programming language, right? So it means that so we need to learn about the syntaxes and then some operators used by programming languages. Okay. So you need to remember. So you need to know the data types used by SystemVerilog. Okay. So and then I mentioned that we normally use logic data type. Okay. So you need to remember that. So we use SystemVerilog or other HDLs for designing hardware. So it means actually when we design a hardware, then our design needs to be translated into real hardware design. So it means that, so actually in chapter 1, we learned that we can implement this digital design using electric circuits. Okay, so we can build the basic logic gate using the CMOS transistors and wires. So we can just connect so transistors using wires, and then this we can also connect input and output ports of a basic logic gate using wires. Okay, so actually these are electric circuits. So when we design our digital system using HDL, then we need to also consider these electric circuit components. Okay, so that's why the SystemVerilog use the logic data type. So it's similar to some digital signal, right? So I mentioned that this logic can have the 4 different values, okay, 0 and 1, obviously, and X and Z, high Z. Okay. Also, we learn how to represent numbers. Okay. So usually our systems, so computer systems also, our systems handle number data. So text data also can be represented using decimal numbers for this digital data, right? So we need to, because we need to represent the numbers in the system Verilog also. And then I mentioned that we can use this format, like, so we can just specify the number of bits, okay? So this is the hardware, and then hardware also includes the hardware resources, and then hardware resources are limited resources, okay? So we cannot increase or decrease the hardware resources at runtime. Okay, so we can just allocate memory space, or we can deallocate memory space. That is some resources in the software, right? In a software code, but in hardware we cannot. So usually we cannot increase or we cannot decrease the hardware resources. So usually, so we need to specify number of bits when we represent the digital numbers. Okay, but it's okay. So even though we do not specify the number of bits, but when this number is assigned to a certain variables, like the bit vectors or the vectors of logic variable, then actually the bit resolution, so that is called the bit resolution. The bit resolution becomes the same to the number of bits of the logic variable. Okay, so for example, so we can declare like this: the logic 3 down to 0 a. So we can declare the logic variable a, and then this a includes the 4 bits, and then we can assign numbers, like assign a equal apostrophe b 0 0 1 1, because it's okay. Anyway, that's not 0 1 1. Okay, so even though we assign numbers like this, because the a has the 4 bits, some component. So actually, the a will have the number like the 4b0011, even though we just assign the 4-bit 11. Okay. So we don't need to, but it is so actually, in order to avoid some bugs or errors, so it is recommended to specify number of bits in the system Verilog numbers. Okay, so it's required. And then okay, we can also use the different bases like the decimal, octal, and the hexadecimal, right? And then even if we do not specify any number of bits or base, then it is handled like unsigned decimal number. Okay. Okay, so now I will explain about the operators of system Verilog. So as you can see, this is the bitwise operators. So what does that mean? So if you see this code, so you can find that. So this module, so this is the module name is the bitwise underbar OPS. So it's the operators. Okay, and then as you can see, this module includes the 2 inputs. So and then this is the bit vector inputs, and then you can find the width. So number of bits assigned to each input. It's the 4-bit inputs. Okay. And then also you can find that there are seven output ports here. And then also the bit width of these output ports. Every output port is 4 bits, right? Then what is the bitwise operator? So you can find the A and B, and then this is the AND gate, right? So bitwise means that is the bit by bit operators. Okay. So we know this is the AND gate, two input AND gate, right? And then AND gate generates some output like this. It's an A, B. But we use the vector, the bit vectors, right? So actually this AND gate. So if we just see the operation, the statement of the system Verilog, you can find that this AND operator receives two operands, okay, two inputs, okay. So these inputs or these operands are vector operands, right? The bit vectors. So it is like this. So this is A0 and then B0, and then this is the AND gate, and this is the Y2, and then the pin number 0, and then A1 and B1, and then this is the AND gate, and then this is Y2, 1, and then A2, B2, and then AND gate, the Y2, 2. So bitwise operator means that this operation is applied to each bit. So and then actually to the same bit location of the two operands, right? So you can understand that this bit operator like this. And so the first Y1 is the NOT operator. So there means that this is the NOT A0, and then NOT A1, NOT A2, and blah blah blah. Okay. So you can find some OR gate and then exclusive OR gate here, and then this is the NAND gate, right? This is the NOT and then AND gate. So actually, this is equivalent to NOT of AND. Okay, so this is equivalent, but we can easily use NAND gate here, NAND operator. Okay, so this is NOR and this is exclusive OR. So we can use the bitwise the logic operators in SystemVerilog like this. Okay. So and then if you see this module, then you can find the assign state. So this is the SystemVerilog syntax. Okay. So what is assign? So you can, so actually when I explain about this, I also use the assign statement here. So it's also some unique statement of SystemVerilog. So in C or C++, so we can just write like this, like A equal 1, right? But in a SystemVerilog, in SystemVerilog, we need to use assign statement. Okay, so it's not allowed. So it can be allowed. So actually, in the test bench, so if we do not consider the hardware implementation, then we don't need to use assign statement. So you can find it like this. So if you see the test bench code, then you can find that the number data is directly assigned to the variable like this. But actually, when you design your own hardware using SystemVerilog, then this module needs to be translated into real hardware. So in this case, if we want to assign a certain value to the logic variable, then you need to use assign statement. Okay. So it is allowed. Even though it is allowed, but you need to consider some hardware implementation, and then you need to use the assign statement. So what does that mean? Assign. So actually, assign represents the implicit continuous assignment. So what does that mean? Implicit continuous assignment. What is different? Like A equal 1 and then assign A equal B. What is different in hardware? So actually in C or some test bench code, if we just write a statement like A equal 1, then it is then at a certain time, the A has the value 1. Okay, and then it is not changed. Okay, but if we use the assign statement, and then usually actually the right hand side is has some other variables. Okay, so this is the LHS, so it's the left hand side LHS, and then this is the RHS, so right hand side. So actually assign means that, so it represented, oh, this is A, and then A is connected to B, okay, using wire. So in a circuit, then if the B value is changed, then A is also changed, right? So if we just connect a certain node using wire in a circuit, it's in the real electric circuit, and then if so this is node, okay, so use node or wire, and then if this voltage level is changed, and then because this node is also connected using wire, the value, like the voltage level, is also changed based on this value. Okay. So assign statement. So it means the implicit continuous assignment. So which means that, so if the right hand side signal is changed, then the left hand side signal is also changed. Okay. So it looks like so right hand side is the driver. Okay, the signal value is the right hand side signal. So right hand side variable is driving a certain value, and then the left hand side variable is also influenced by the driver. The driven signal by the right hand side variable. This is the assign statement. So it's a little bit different. So if we just write a statement like A equal 1, then it's the one-time change. Okay, so it's the one-time change. So at this time, then the value is the right hand side value is assigned to this variable. But if we use assign statement, then the left hand side signal is continuously driven by the right hand side signal. It's a continuously. So then you need to understand it like this. If the right hand side signal is changed, then the left hand side signal can be also changed or influenced. Okay. So this is the example. So Y2 is so what A and B, and then I also use the assign statement. So what does that mean? So input port A and B is connected using the AND gate, and then the output, the Y2 becomes the output of this logic gate. So it means if the input signals are changed, right? The input signals can be changed by time. So this is hardware. Then output signals are also changing based on the logic. So logic gate. or operations. This is the assign statement. Okay, so you can understand. Oh, the right hand side is changing. Then the left hand side is influenced by the changed values in the right hand side signals. Do you understand? So this is the some unique feature of SystemVerilog. So it is because you need to know that we use SystemVerilog for hardware implementation. Okay, so that's why some statements are so unique in SystemVerilog or HDL. Okay, so this is the assignment. Okay, so this is very important concept in SystemVerilog. Okay, because it's a unique. Okay, so I hope everyone can understand the meaning of assign statement. So okay, and then I will introduce about the reduction operators. So in this example, you can find that this module has the one input, one bit vector input, and then actually the 7 output ports, but as you can see, the Y1 is the bit vector output, and then Y2, and then Y2 from Y2 to Y7. So these outputs are one bit output. Okay, and then also you can find some operator here. So this is the NOT, and then this is AND, this is OR, then exclusive OR, the same, but so what is different? Actually, in the bitwise operators, so we use the operator here, and then this operator has two operands. Okay, two input values. So that is the operands. Those are operands, but the different. So in this statement, you can find that this is just the AND operator, and then after that, AND operator is followed by one operand. Okay, A. So it's a different. Even though the operator is the same, okay, so actually the same AND operator, but if this AND operator has two operands, that is the bitwise AND operation. But if the AND operator has one operand, then this is the reduction operator, reduction AND. And then this is the meaning of reduction AND. So, okay, so what is the meaning? So this is the A3, A2, A1, A0, and then actually we have 4 input AND gate, and then this becomes the Y2. So this the reduction operator and this statement represent this logic gate. Okay, so because this input signal is the bit vector logic, so actually, and then we just AND the all input bits and then generate the output signal like this, and then we use the AND gates. So this is the meaning of reduction operator. So you can find the reduction OR, reduction exclusive OR, and then NOR and exclusive NOR. Okay, so and then these are the meaning of this reduction operator. So also you can also check this NAND gate. Actually, the meaning of that is reduction NAND is it's equivalent to the overall NAND. Okay, so it looks like this gate. Okay, okay, do you understand? So it's not A3 NAND, A2 NAND, A1 blah blah blah. It's not. So it's just the overall NAND gate. Okay, so it looks like this logic gate. So and then this reduction operator has higher priority than bitwise operators. So we will learn about the priority of operators later, but you need to remember that reduction operator has higher priorities than bitwise operators. Okay. Okay, and then also the SystemVerilog has the conditional assignment, like the question mark. So so this is very convenient. So actually in C we frequently use this ternary operator. So like the A question mark and then B C. So this is the if then else, right? It means that if A is true, then B is selected. Then if A is false, then C is selected. So actually C has the same operator, right? So SystemVerilog has also the same conditional assignment operator, okay, like this, okay? So this is Y, and then also you can find that this is T1 and T2. There are two input bit vectors, and then this is the selection signal, okay? And then T1 and T2. So if this value is true, then Y equal T1. The T1 is assigned to Y, and then if this value is false, then Y equal T2. T2 is assigned to 1. But you can think, oh, S is the logic. S is the logic. But it has the 0, it can have 0, 1, X, and Z. But why? I said that if this is true, this is false, then Y equal T1 or T2. What does that mean? So it's equivalent to C actually. So in C, 0 represent false, right? And then non-zero represent true, right? SystemVerilog is the same. If S is 1, then means true, right? If S is 1, that means true. And then if S is 0, then means false. Now how about X or Z? Actually, it's not defined. So it means, so actually, this statement can be implemented like this. So actually, this is the multiplexer. Okay. So based on the selection signal, the output Y can be connected to the D0 or D1. So this is the it's called this component. This component is called a multiplexer. Okay. The multiplexer means that using a selection signal, we can select the one of inputs to output. Okay, so this is the multiplexer. So this is the real hardware. Okay, so it means that if the selection signal becomes the high Z or contention like X, then actually we cannot determine the true value of this output. So actually, so if S is 0, Z high Z or X, then the output becomes X, so unknown. Okay. So I use the here. So you can understand that if the S is 1, S is true, and then S is 0, that is false. Okay. So this is the ternary operator. And then so we can using this ternary operator then we can easily implement actually multiplexer. Okay, so it is equivalent to if then if else of the C or C++. Okay, and so you need to remember that the ternary operator. So this is called the ternary operator, the conditional assignment, because it has three operands. Okay, so until this slide, so I just showed that the output is directly connected or directly connected to the input signals, or the input signals are connected to the logic gate, and then the output is directly connected to the logic gate of input signals. But we can also use the internal variables in a SystemVerilog. Okay, so actually our design is very complex. So our design will include many nodes. Okay, so then we can define the internal nodes like this. So this example shows the adder logic. So you can find that there are 3 input ports and then 2 output ports here. And then I define the internal signal or internal nodes P and G. Okay. So, and then the internal node can be assigned like this: A exclusive or B, and then A and B. Okay. So this is the internal node, and then using the internal node, we can assign the signals to output port. So that can be possible. So actually our design is very complex. So our design will include many internal nodes. So you can declare the internal nodes inside of the module, okay, using the logic variable. So this is the synthesized output. Okay, so you can find the input ports here, and then so P is the A exclusive or B. So A and B pass through the exclusive OR gate, so this becomes the P, right? And then the G is the A and B, so you can find the AND gate here. So this node becomes the G. And then using by combining the P, G, and then also C in, so you can find the C in here, and then the P pass through the AND gate, so here, and then it becomes the, here's the some not that is so some internal node, but this internal node is not declared in the SystemVerilog, right? So, and then actually the P and C in pass through the exclusive OR gate, so it becomes the S. And then this S is connected to the output port. So even though this node is not declared, but it's okay, because you can find the C out is the G OR and then P and the C in. Okay, so you can find the AND gate here and then OR gate here. Okay, but when this module is synthesized, then this module can be synthesized into like this. Okay, so let's talk about the priority of SystemVerilog operators. So in this table shows the priorities of SystemVerilog operators. Okay, so the upper entry shows the highest priority, and then the lower entry shows the lower priority. Okay, you can. So also when we learned about the operator of program languages, and then so every program language also defines the priorities of operators, and the SystemVerilog is the same. Okay, so this is the priorities of priority of operators. Okay, you can find those many SystemVerilog operators here. Okay, so you can find some comparison operators here. Okay? So it's okay. So because we know that AND gate, so AND operator. So if you see this table, so you can find that the AND operator has the higher priority compared to OR operator. It's the same, right? So when we write a Boolean equation, the AND is represented using multiplier, and then we use the addition operator for representing OR gate. And then we learn that the AND operator, the multiplication, has higher priority than addition, the plus operator, OR gate. So it's the same. It's the same to SystemVerilog. So it's okay. So if So in this statement, the OR gate has the lower priority, and then AND gate has the higher priority, right? So which means that if this statement is synthesized, then it will be synthesized like this P and C in, or this is AND. So AND gate, AND operation needs to be computed first, right? Because AND operator has higher priority than OR operator. Then, so G OR gate is connected. So this is the C out. Okay. So based on the priority of the SystemVerilog, this statement will be synthesized using AND gate first and then followed by OR gate. Okay, it's fine, but it's not recommended. So actually it's the same to the any programming languages. So actually we know the operators in any programming languages have their own hierarchy, right? And then it's the same to the SystemVerilog. But sometimes we may make bugs. Okay. The problem is that we may intend like this in this statement and then end the game. Okay. But we may, so by mistake, we may write the code like this, but then this code will generate incorrect circuit or incorrect hardware. So that's the problem. So I recommend you to use the bracket like this. Okay. So even though the AND gate has the higher priority, and then everyone knows that, but in order to avoid some bugs or mistakes, then you are recommend to use bracket for every statement. Okay, it's very important. So when you write a code using any programming languages, then you need to avoid any possibility of bugs. Okay, so the SystemVerilog operator has its own priority. Actually, so based on some priority level, then we can write the code like this, but it's fine, but it's not recommended. Okay. Actually, it is true for the C or C++, Java, any programming languages. Okay. Okay. So also, SystemVerilog has the replication operator. So what does that mean? So sometimes we can write the code like this. So this is the example. So this is the input. It's a one input. So this input has the one bit data, 1-bit signal, and then the output has the bit vector data. Okay, so this is the output Y has the 4-bit signal, and then so actually it's A and this the A is connected to the Y0, Y1, Y2, Y3. Okay, so it means so A is replicated, and then the A actually the same value A is connected to the some different bit of output Y. So this can be possible because so we are making hardware, and then so which means that it can be also possible. The driver is the one driver, like this AND gate. So this input can be delivered to multiple node. Okay, that can be possible. This is the hardware. So a same signals, a same node can be connected to the multiple inputs of the different logic gate. That can be possible. So SystemVerilog has the replication operator. Okay, so the replication operator has some number here, and then we use the bracket, and then we can use the signal name, the variable name inside of the bracket. Okay, then this signal or this variable is repeated n times. So this is the example. This is the input A, right? The input A is repeated 4 times, and then assigned to the each bit of Y. So this is some implementation. The A signal A is connected to the different bits of output port Y. Okay. And then also SystemVerilog has the concatenation operator. So concatenation. So this is also example. So this module has the 2 inputs A and B, and then each input has 2 bits signal, and then Y is the 4 bit signal. So and then concatenation, for the concatenation, so it's similar to the merge. So okay, so concatenation means that the signals can be merged. Okay, so and then we can use the bracket for concatenating 2 signals. So what does that mean? So the Y has the 4-bit signal. So this is the Y0, Y1, Y2, Y3. Okay, so then the A is assigned. So then what the A is the 2-bit signal. So it means so A0 is assigned to Y0, and then A1 is assigned to Y1. And that's it, because A is the 2-bit signal. Then the B is concatenated. So B is here. So B0 is assigned to Y2, and then B1 is assigned to Y3. So sometimes, so you may think that this is not necessary, right? But sometimes we may define some different nodes, and then the different nodes can be assigned by some different input signals, so different inputs. Okay, so just remember that this is the concatenation. Okay, so it means it represents this assignment. Okay, this is some summarization of the concatenation, and then some replication. So this is so this in this module, this module includes the 2 input ports, and then each input has the 3-bit signal, and then Y has the 12 bits Y is the 12-bit output port. Okay, and then so Y is assigned like this. So what does that mean? So this is the summarization. So in this example, we can know that, oh, this is the bracket, okay? So it's a concatenation. So what are concatenated? So inside of the bracket, and you can find that A 2 down to 1, and then, oh, this is the B0, but it's repeated 3 times, and then A0 and constant value. So this is the 6-bit signal, and then base is B, and then 10 underscore 0 underbar 0010. So actually it is equivalent to 6 underbar B, 6 apostrophe B 100010. Okay, so underbar is just for the some. So it's just for used for underbar is used for just formatting, but it does not have any meaning. So this is just for formatting, because the binary value. If we use the binary value, then it is very long. So it's not easy to figure out some position of this binary numbers. So we use the underbar, so underscore, so to indicate the position of the binary value. So usually we use the underbar for every 4 bits. Okay. So if we use this underbar, then we can easily figure out the position or bit digit of this binary number. Okay. So you can use the underbar here. So what does that mean? So this is the concatenation operator. So firstly, the constant value. The constant value is assigned to Y. Okay, so which means that Y0, what's the value of the Y0? Y0 is 0, right? Y1 is 1. Y2 is 0, right? And then this is the 6-bit value. So A0 is assigned to Y6, right? Okay. Then after that, the B0 is replicated 3 times. Okay. So Y7 is B0, right? Y8 is also B0. Y9 is also B0. After that, A2 down to 1 is assigned. So Y10 is A1. Y11 is A2. Okay. So in this example, I used the concatenation pointer, the bracket, the large bracket. So inside of this the bracket, then some signals are included. Okay. Also inside of the bracket, then we can also find the replication operator. Okay. So this B0 is replicated 3 times, and then also the constant value, the constant number can be also included. So you need to remember that underscore. You can use underscore or underbar for some formatting. You can be used for formatting, okay? Because because the binary number, the binary number is very long usually. Okay, and then system Verilog actually ignores it underscore. Okay. So you may think that the SystemVerilog has it's unique operators, many unique operators, right? Sometimes, but it's true. So every system, every programming language has its own operator, unique operators, right? So and then actually when so if you want to learn about the programming languages, then actually you need to also memorize. You need to memorize the meaning of operators. Okay. Okay. So this is another example, like the plotting output, and then it can use Z. So we learned that Z represent high impedance or disconnection. Okay, and then we also learned about the tri-state gate. Okay, what is the tri-state gate? So A is connected to B, but this is the enable signal. And then based on the enable signal, if the enable is 1, then B equal A, but if enable is 0, then B is high Z. So this is the tri-state gate. So this is also hardware. And then, so it means that the SystemVerilog also needs to support for implementing tri-state gate. Okay, so it means that the SystemVerilog also needs to include Z, high impedance, or disconnection. So this is the example. So you can find the input here, and then enable is the control signal. So it controls the connection or disconnection in the tri-state gate. And then Y is the output. So this is the ternary operator, right? So it means that if the enable is true, so which means that if the enable is 1, true, then Y is A. So A is assigned to Y. Then if the enable is 0, is a false, then this is assigned. Y is the 4-bit Z by Z. So this is the tri-state gate. Okay, so it's possible. And then if we just write the code, the SystemVerilog code like this, then tri-state gate will be implemented. It will be synthesized. But you can find some different data type here. So in this example, you can find A is the logic data type, right? It's a logic, and then enable. So enable signal is also logic data type. And how about the Y? Y is the tri-state. Okay. So in order to implement the tri-state gate, then we need to declare the variable as tri-data type, tri-state data type, the TRI, tri-state. It means the tri-state. So you may think that, logic gate also, the logic data type also can have high Z. So that's what I explained, right? The logic gate also represent the logic data type can represent high Z also, but actually in SystemVerilog, the logic A, B, and then so A is here and B is here, and then Y is here. Actually, if we just declare a certain node as logic data type, then actually in a system Verilog, this is not allowed. So what is this case? So A, the node A is connected to the node B, and then the node A and node B are both driving output Y. So, and then, in this example, the A and B are declared as logic data type. And then this case, this is not allowed in a system Verilog. So this is an error. Okay. So then how can we implement twi-state gate? So if we use the twi-state gate like this, so it's A and this is the enable 0, then B, this is the enable controlled by enable 1, this is 1. So if we use twi-state gate like this, then actually this is possible. It's okay. Actually, we can use twi-state gate for implementing common bus. So actually this is called bus. Then this bus is driven by multiple nodes A and B, but the driving of these multiple nodes is controlled by enable signal. So this is actually possible in a system Verilog. But problem is that in a system Verilog, if we just declare this gate, right? So this is the kind of Y, X, and we can declare this node like the X and Y, X and G, not G. G is not allowed. I'm sorry about that. So we can declare this node like the C and D. Okay. So if we just declare this node using logic gate, logic C and D, then it's not allowed. Okay, in a system Verilog, because C and D node is both nodes are both driving output Y. Okay, so in order to avoid this error, we need to declare this node using twi data type C and D. Okay, so that's why the output Y of this module is declared as twi data type. So it means that this node, this output can be connected to multiple nodes. Okay, so then we need to declare this node using twi data type. Okay, so this is important. Logic can only have a single driver. Okay, so if we just implement the circuit like this using logic data type, it's not allowed. Okay, then in order to implement the twi-state gate, then we need to use the twi data type. Okay, so this is the end of the system Verilog part. So this is the first part of the system Verilog. Okay, so and then actually, so if you see the last slide of the every chapter, then you can find that the chapters covered by my slide. So actually this slide includes the chapters 4.1, 4.2, and 4.3 of our textbook. Okay, so it means, so actually I announced that our midterm will cover the chapter 1 and chapter 2, and then system Verilog part, which means that our midterm will also include the chapter 4.1, 4.2, and 4.3. Okay. 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 So okay. So I just explained about some basic concept, and then some basic operators, and then basic syntaxes of SystemVerilog. So, and then we are going back to the combinational logic. Okay, and then so in this chapter, this chapter is different from the chapters in the our textbook, but in this slide, then I will introduce about some basic combinational logics, combinational blocks. Okay, so I will just explain about some frequently used combinational blocks. Okay, so what is the combinational blocks? So we learned about the basic logic gate, like the AND gate, OR gate, NOT gate, NAND gate, blah blah blah. And then actually, so basic logic gates are combinational logics, right? So it is because the output of basic logic gate can be only determined by the input signals, right? So that's why the basic logic gates are combinational logic. But in a real hardware, we frequently use a certain the basic blocks. Okay. So and then these blocks. So actually, so we'll also learn about some basic blocks for the sequential logic. So before the midterm, so we will learn about the combination of basic blocks. Okay. So combination logic or basic logic gate can be grouped into larger building block, and then to build more complex systems. 이거 블랙보드에 올라왔죠? 아니에요? 올라왔죠? Okay, so and then so by combining multiple logic gate, we can make the basic logic gate, and then these basic blocks, basic combinational blocks, and then these combinational blocks can be frequently used and then frequently implemented in our digital systems. Okay, so these are the examples of the combinational blocks: the full adders, private circuits, multiplexers, and decoders. Okay, so I will explain about the multiplexers and then decoders. The multiplexers. So actually, when I explained about the ternary operator in SystemVerilog, I already explained about the multiplexers. So this is multiplexer, or then it is also called the MUX. MUX, MUX. So the meaning is that actually, so the multiplexer has multiple inputs, and then multiplexer has one output. Then based on the selection signal, is the control signal, the output can be connected to one of multiple inputs, which means that one of multiple inputs can be assigned to output based on the selection signal. Okay, this is the multiplexer. So this slide shows the example of a multiplexer, and then this multiplexer is called the 2-to-1 multiplexer. It is because this multiplexer has two inputs, like D0 and D1, and then one output. So using this multiplexer, we can select one of two inputs, and then the one of two inputs is assigned to output. Okay, the first number represents the number of input port, and then it is actually the output of the multiplexer. Okay, so then N1 MUX or multiplexer represented. This multiplexer has n inputs and then one output. So this is the truth table actually. So actually we just learned about the meaning of the multiplexer, and then so if we just consider this multiplexer, and we can find that, oh, this multiplexer has the 3 inputs as and D0 and D1, and then 1 output. So we can make a truth table like this, right? So, and then you can find that if the S is 0, what is selected? D0 is selected. So you can find that the Y is equivalent to D0 if the S is 0, right? Otherwise, if the S is 1 here, then D1 is selected, so Y is equivalent to D1. So we can simplify this truth table like this. So S, based on the S, Y becomes the D0 or D1. Okay. So we can, which means that using the truth table, so we can implement the Boolean equation of this multiplexer. So using the SOP form. Okay. So in chapter 2 covers the Boolean equation, and then it means that the midterm will also cover the SOP form of the Boolean equation from the truth table. Okay, so this is the truth table, and then so you can make the kernel map based on this truth table, and then we can cover these elements, and we can make implement some logic gate like this. Okay, so if we use the SOP form, actually the multiplexer can be implemented like this. So it's the AND gate, and then this is OR gate, and then actually you can find that the S is connected to this AND gate, and then S bar. So this is the NOT gate. The S bar is connected to this AND gate. So actually, so S, A, and B. So we can think that based on the S, if the S is 1, then B is A. Okay, then this A is selected. So we can understand the multiplexer like this, using the SOP form. Also, we can implement the multiplexer using tri-state gate like this. Okay, so what does that mean? So this is the tri-state gate, but you can find the bubble here, and then S is connected to this bubble. Okay, so this is D0 and then D1, and then S is directly connected to the D1. So actually, this is the S. Okay, so if the S is 0, then S bar is 1. So this tri-state gate is enabled. This is not enabled. So Y is connected to D0. If the S is 1, right, then S bar is 0. So this is off. This tri-state gate off, and this is enabled. So Y is D1. So we can implement multiplexer using tri-state gate. Okay, but you need to remember that when the tri-state gate is implemented, then actually two tri-state gates are connected to the output Y. Then this tri-state gate needs to be turned on exclusively. So which means that only one tri-state gate must be turned on. Okay. If the multiple tri-state gates are turned on, what will happen? It's contention, right? Multiple tri-state gates are turned on or enabled, it's contention. Okay, we need to avoid this case. Okay, so I will stop here. Okay, so any question? Okay. Thank you for your attention. See you in the next class. 화요일 날 수업 있습니다.